On behalf of TDJ, we'd like to welcome everybody for setting aside their valuable time to spend about 30 or 40 minutes with us here this morning. Just as a quick overview, what we're going to do is after we go through the presentation, I'll be prepared to address any questions that you might have. If you look in, should be in your upper right-hand corner of your computer screen, there's going to be a dialog box where you can submit questions. Feel free to submit your questions throughout the presentation, and at the very end of our presentation, which again should last about 30 minutes, I'll be prepared to address those questions. If it's a public question that you don't mind me addressing the question as well as the answer, submit it through this channel and we'll address it at the very end. If it's more of a private nature question, like you've got a question about a specific project you're working on or you're bidding on, and it's a little more private in nature, then you'll see that we've got our email address listed here at tdj@blastox.com at the very bottom of the screen that you're looking at, or feel free to call us at 800-252-7869. And just as the high-level overview, a couple of things we're going to be discussing today is we will be discussing some of the benefits of Blastox, which is a heavy metal stabilization reagent, but we really also hope to provide some educational information, including the different types of stabilization techniques that are out there, some different application and mixing techniques. We're going to talk a little bit generically about heavy metal solubility, in hopes to impart some knowledge generically about those kinds of systems there. So without any further ado, we're going to go ahead and jump into the seminar here. So the very first question I'd like to address first is, what is Blastox? Well, Blastox is a complex calcium silicates chemistry. It is a dry granular product, so it contrasts obviously with a liquid material. And for application on a job site, it tends to be a lot less messy when you're dealing with a dry granular material. A benefit of our production facility is we have the ability of manufacturing this product in a number of different particle sizes. Our three specific particle ranges are a -16 to a +50 mesh material. That's really a large sand size product that's used for sandblasting that I'll get to here in just a minute. We also have a finer particle sizing material that's a -50 to a +400 mesh range. That is our Blastox 215 material that is a product that's used quite a bit for soil application projects. We also have an even finer grade of material where everything is -300 mesh material. It is a very finely graded material that's intended to be injected into ventilation systems, so the fine particle can be entrained so that it can commingle with materials or waste that are being generated from our foundry industry. And those smaller particles then commingle with the dust coming through that ventilation system. So when they get into the back house, they're already thoroughly homogenized so that they can react with the heavy metals. We have three standard packaging types, 70-pound paper bags that have a plastic liner in between the multi-walled paper materials. We have 3,000-pound super sacks, and we also have bulk capacity as well. 3,000-pound super sacks tend to be the packaging of choice for most contractors because it's easy for them to apply it on the job site and to store it if they don't have a large silo on site. Now, the Blastox material can work on a wide range of RCRA 8 materials, but it was specifically designed to target lead and cadmium. We can, as this last bullet point does imply, we can add additional enhancements if we're working on other materials that would be present as a multivalent state, possibly. A very good example is chromium in a form of hexavalent chromium. where those materials require a reduction, oxidation, additional step before the Blastox 215 can further stabilize that material. And just moving from left to right, these again are the 3 specific products that we manufacture, but we can also custom blend these materials together, and we also have the ability of producing additional particle sizing based upon what the application would be. Moving from left to right, the Blastox material is a sand grain material, which is used for sandblasting of lead-based paints. Water towers, petrochemical storage facilities, bridge structures that were painted with lead-based paint a long time ago create a toxic waste when removed. Our material is blended with various types of abrasives so that the Blastox material chemically reacts with the lead-based paint, rendering it non-hazardous for local Subtitle D disposal. The middle product there, Blastox 215, if you look around the perimeter of that pile there, you can almost see pepper-like flakes. This is a material that is primarily used for soil application. And then on the right, you can see it's a very powdery material that's more used for injecting in ventilation systems so the small particle can be entrained. It's interesting to note that we recently did a project out in New England area where the Blastox 215 had the lowest dose rate, but we actually did a blend of the Blastox and the Blastox 215 where it took the add rate from 3% up to 4%, but we used larger grains because this was in a very sensitive, highly urbanized downtown area, and dusting was prohibited. So we ended up coming up with a blend for them that required a slightly higher dose rate, but achieved their goal of TCOP compliance, as well as keeping dusting to a minimum so there weren't any on-site issues or concerns. This next slide here is more of a generic listing of 3 different ways that you can achieve TCOP compliance, specifically with heavy metals. Any one of these 3 can be effective. As we'll find out, you need to be careful about which of these 3 you're relying upon. This first one here is you can add materials like calcium oxide or magnesium oxide or alkaline materials to a TCOP test, and you can increase the pH to decrease the solubility of heavy metals. I'm going to flash forward here to a graph just to show you what metal solubilities would look like. If you look up at the very top, we've got lead hydroxide, and if you drop the arrow down at the bottom of the lead hydroxide curve, you'll see the minimum solubility range is about 9.5. If you look over to cadmium, which is the other heavy metal that Blastox is designed to attack, you'll see that the minimum solubility range for cadmium hydroxide is 11. So keep that in mind as we go back to the last slide, where you can achieve TCOP compliance by simply adding a calcium oxide or a mag oxide based material to put the TCOP solution in that minimum solubility range. Now, I would caution you on just relying upon that way to achieve TCOP compliance, because once the buffering capacity goes away, in my view, it's not a matter of if, but when that buffering capacity gets eliminated, unless you have something else there to keep the heavy metals from going into solution, you could have a future leaching issue. So we have pH adjustment in the first bullet point. The second bullet point that we have here is about chemical conversion, where you're actually creating a new heavy metal compound that's less susceptible to leaching. This is more of a long-term permanent ability to ensure that the heavy metals never leach again in the future. A third way to do that is there are materials that are out there which you could create a block, if you will, and the block of the waste matrix is effectively encapsulating the waste material so that you have a physical barrier helping to minimize the solubility or the release of those heavy metals. Now, ideally, you'd have a material that would adjust the pH. You would have a material that would create a new chemical compound for long-term stability. And you would also have the third safeguard, where you're also creating an encapsulated waste to help to minimize future leaching. When you have all three of those, what you've really got is a good mousetrap that has multiple safeguards. And again, the goal there is you're reducing future liability for your property, or if you're a consulting engineering firm, you're helping to reduce liability on behalf of your client. I'm happy to say that Blastox incorporates each of these three safeguards, and in combination helps to assure that you have a long-term stable waste material. And this is a graph that I had reviewed earlier, so I'll go ahead and move forward on that. The key part of this, however, is keeping in mind heavy metals, certain heavy metals do have the ability to leach at high pH values and low pH values, as is the case with these large U solubility curves. The term for that is called amphotericity. So amphoteric means heavy metals leach at high pH values and low pH values, but have a minimum solubility range, in this case, between 9 and 11. Now I'd like to talk a little bit about and provide some knowledge about the two types of soil leaching tests that are most encountered. The TCOP test is probably the most renowned leaching protocol that's out there, because that's the de facto test to determine if a waste is hazardous or not hazardous. The TCOP test, if you look at that acronym, it's toxicity characteristic leach procedure, or in the field, we'll hear it called the TCLIP test. The actual EPA test method is 1311. Basically what this leach test is it uses two different types of leaching medium, depending upon whether or not the waste is alkaline. If it's a non-alkaline waste, they'll use extraction fluid number 1, which has a pH of 4.9. If it's more alkaline, and they determine this by doing a small sub-test or sub-sample of the waste that was sent in by adding some hydrochloric acid to materials, 5 grams of the material that's been added to 100 milliliters of deionized water, and then based upon how it responds to the dosing of hydrochloric acid, they either add extraction fluid number 1 or extraction fluid number 2. Both extraction types are acetic acid based. So this test, if you think about how this test is working, it's got 2 liters of acid in a large container containing 100 grams of the sample, and it's rotated for about 18 hours. And then at the end of that, the materials are filtered, digested, and analyzed for the amount of leachable or soluble heavy metals in this instance. The other test that is less frequently used, but it's a test that achieves a different result, and that different result is it's just not a matter of do we comply with the regulatory guideline of 5 milligrams per liter for lead in this instance, or is it a test that's designed to determine long-term stability? Well, as we go through the explanation of the multiple extraction procedure, it should become apparent that this test was specifically designed to eliminate buffering capacities that I mentioned earlier that a calcium oxide or mag oxide material could provide. It's intended specifically to eliminate that buffering capacity. And here's basically how it works. It is EPA test method 1320. There's just one extraction fluid that is sulfuric and a nitric acid blend. Keep in mind the TCOP test was an acetic acid blend that had a pH of, it had 2 different extraction fluids. Well, this material, when the waste, you still take 100 grams of waste, you put it in your vessel with the acetic acid, but instead of running one cycle, it's actually 10 cycles. And instead of each cycle being 18 hours, the cycles here are 24 hours. So after you analyze it the first time, you take that sample that's been ran through the acid bath once, and you put it back into a fresh bath of acid for another 24 hours. So our extensive experience with this is by the third or fourth extraction, if you're simply adding a pH buffering material, you're going to eliminate that pH buffering material. And if there's nothing else there keeping the material from going into solution, then what you're going to have is a potential future leaching condition. So the third bullet point here is very important because this test was designed by EPA to predict the long-term stability of waste by eliminating the pH buffering. Now, as I alluded to earlier, you can achieve a pass on the TCOP test. However, it does require some very careful dosing. And in the field, because things might not be as precise as what they are in a lab, you have to be very careful about how you do that, because if you add too much, you could actually cause the materials to leach at a higher rate than what they were before you added anything. So the summary of the MEP test is it was designed as a long-term stability test, but specifically designed to eliminate the pH buffering effect. As I alluded to earlier, Blastox does have a pH buffering effect. That was one of 3 safeguards, but I can tell you that Blastox will pass and has passed many multiple extraction procedures. So having talked a little bit about generic ways to stabilize a waste and how the Blastox material itself would work, talked a little bit about the various types of testing protocols that are out there. Now I want to talk a little bit about how much reagent to add. Clearly, I'm representing TDJ and Blastox as a material that we manufacture, but really these next set of bullet points I'm going to go through, this would be applicable whether you use Blastox or some other type of powder reagent. So the first thing we would prefer to do is get a sample and do testing. As I mentioned earlier about the project up in New England, we had the ability to obtain samples that they had collected during site characterization, and they had sent us a sample from the highest contaminated area. We've done the testing and determined what the dose rate was. If it's pretty homogeneous, we would just recommend that we get 1 or at most 2 samples to do testing. If you have a high degree of variability, let's say we have areas where it's greater than 100 milligrams per liter and an area where it's less than 100 milligrams per liter. If it's a very large project, sometimes it makes sense to segregate those because you can hit one with, let's say, a 4 or 5% dose rate if it's greater than 100 milligrams per liter, and we can get down to 2 or 3% for areas that only leach 5 to 50 milligrams per liter. So if we have high variability and we really want to optimize the dose rate, we would need a sample from each area, and we would need about 1 quart of each sample. And as the first bullet point alludes to, we provide that testing complimentary, meaning that we will pay for that testing because we want to demonstrate to you that the material is effective. And as I kind of glossed over, these are general ranges of the amount of our material based upon looking at a lab report in the event that samples aren't available. As I said, if it's 5 to 50, 3% has proven to be very effective. If it's 50 to 100 or more, 5% has also demonstrated to be very effective. But I do want to point out the project that I was mentioning up in New England, it leached at 180 milligrams per liter, and we successfully stabilized it to non-detectable levels. It was below the reporting limit for that particular lab with only a 3% add rate. So I've tried to be conservative here and give you some general guidelines, but many times the material can work at even lower add rates than what we have listed here. So please keep that in mind as you're looking on existing projects or any upcoming projects. Now, I know it's in the morning and maybe we're not prepared to do any math exercises here, but if you can just bear with me for just a moment, I wanted to review how we actually calculate how much material, because there's two ways of doing it. The way I'm going to go through here is a preferred way to make sure that you have an accurate amount of material used on the project site. The larger the volume, the more critical it is to make sure we calculate how much material to add in this fashion. So we tend to sell our material on the tons metric, and most contractors and consultants look at a different metric, and that's cubic yards. So the first thing that we do is, if you've got a specific conversion factor because you've got good geotechnical knowledge of the soil, apply your conversion factor. Generally, we apply a conversion factor of 1.4, and then after we convert from cubic yards of soil to tons, you're going to take that tons and divide it by 1 minus the add rate. So this add rate here was 3%. So what we'll do is, the example is 10,000 cubic yards of soil, and we have a 3% add rate. If we multiply the cubic yards by 1.4, we have 14,000 tons. Now, if you just multiplied 14,000 tons by 3%, you would get 420 tons of reagent. So keep that in mind. And then if we do it in this calculation, we take 14,000 tons and we divide it by 1 minus the add rate in decimal form. Here the add rate was 3%, or 0.03. So it's 14,000 tons divided by 1 minus 0.03, which is 0.97. 14,000 divided by 0.97, we have a total, which includes the chemistry and the soil, of 14,433 tons. Subtracting that from the original calculation of 14,000 tons of soil, and we have a product of 433 reagent tons versus a 420 tons if we simply multiplied that. So that's a little bit of a mathematical nuance, but we believe this is the best method to calculate that, to make sure you're applying the right amount on the job site that we've been able to do on a bin scale basis. So I'm going to go through a couple of examples here of how to mix the Blastox material, and then I've got a set of about 9 or 10 slides that go through 3 different projects, giving some pictures showing how people were actually able to take this concept and then using it out in the field. Got a couple more slides that give a good flavor for the types of heavy metals and what the add rate was, given what the leachable rate was for the heavy metals. We had a project down in the St. Louis area that was a former auto assembly plant. They had an E-coat application process that was set up that required lead to be present in those materials. And then they generally just had a burn pile area where this predates EPA and the existence of a lot of waste management regulations. So as a result, it was very common to put them all in one large hole in the ground or a trench and burn them. Well, that's what happened here. But as that property became potentially more valuable from real estate in the area going up in value, they decided to clean up the area. Well, they did testing to determine that lead leached at greater than 100 milligrams per liter. At that high rate, we tested it and did a treatability study and determined that 4% of our standard Blastox 215 was quite effective. In a similar application, but in a different urban setting, this one up in Chicago area, where they were going to build a school, which if you think about an elementary school with children, immediately the term sensitive receptor pops to mind, because you certainly want to make sure you don't have any lead in the area, and you want to make sure that's been thoroughly cleaned. So this, we thought, was a very good project for us because of its unique nature with having a school built on top of this property. Well, it was a wide range that we had, from a low of 6.3 milligrams per liter for lead up to almost 200 milligrams per liter. So again, keep in mind the slide where I'd said 50 to 100 may need 5%. Again, I try to be conservative there, and you can see here that ranges that exceeded that, we were able to stabilize it with a 4% average dose rate. And that concludes our webinar here today.